Hey team, this is Mrs. Hunter. So I figured an explanation at this point might be helpful. So Kw stands for the equilibrium constant of water. As you'll recall from the earlier slides, water breaks apart, right? It disassociates and it goes back and forth. And so it's in a state of dynamic equilibrium. And that's actually where this big K with the little w comes from. Now, you don't need to worry about that too much. We don't really talk about equilibrium in Chem 1, but we are going to use its application to do some calculations. So hopefully you remember from earlier, you can't form a hydronium without forming a hydroxide as well, right? Because if one water is gaining a hydrogen, where is it gaining it from? It's gaining it from another water, which is losing it and turning into hydroxide. So in pure water, the values of hydronium and hydroxide are always equal. And I hope you also remember on the slideshow, it says this only happens to a very, 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 very small amount of water. How small? Super small. So when it's actually studied to figure out the concentrations, 1 times 10 to the negative 7th molarity, right? So that's 0.0000001 mole per liter of solution. It's a very, very low concentration. So when you're drinking pure water, this is neutral because you have equal amounts of both of these, and it's a really small amount. Like, this is not something you're normally going to notice. So the cool thing about knowing these values, when we look at equilibrium constants, so if you take AP Chem, we'll definitely talk more about that, you would multiply the two concentrations. And when we do, because these are the concentrations that they always are, when we multiply them, we get a constant value, 1 times 10 to the negative 14th. This value is going to be super helpful for us. So, quick summary. These are experimentally determined that in pure water, when you don't have anything else dissolved in it, these are the concentrations of hydronium and hydroxide. And when we multiply them together, we get the equilibrium constant of water, which we abbreviate K with a little w. So the cool part about this is when we make a solution with an acid or a base, right? So we're going to dissolve that acid or base in the water. Now's where it gets interesting. So when acids get dissolved in water, you're going to see more hydronium. And I think that makes sense to you. You'll remember when we looked at acids, acids always had a hydrogen that they could give away, right? So if an acid is being dissolved in water, you might remember when we did Bronsted-Lowry that you're going to get hydronium, right? And then you'll be left with whatever else. So in this case, whatever else would just be the conjugate base, which would be X with a minus. So we've increased the amount of hydronium. So the amount of hydronium dissolved in your solution, the concentration of it has gone up. Now the opposite is occurring with bases. When bases get dissolved, we're going to see that there's going to be more hydroxide. So some of these are really straightforward. Like when you look at your strong bases, for example, like NaOH, well, of course, when it breaks apart into its respective ions, you get Na plus and OH minus. So we've increased the OH minus. Other ones, we really need to understand the Bronsted-Lowry equations to really understand how they work. So for example, when you look at NH3 and we dissolve it in water, remember, it's a base. It can accept hydrogen, so it becomes NH4 plus. Where did it get that extra hydrogen from? Yep, the water, which means the water turns into hydroxide. And ultimately, what have we done? Bases increase the concentration of hydroxide. So I always like to explain that this is like a balancing act. So when you've got pure neutral water, think right there, you have equal amounts of hydronium and hydroxide. But then if you've got something that causes you to have more hydronium, what's going to cause that is something that acts acidically. And what makes something an acid and a stronger, more dangerous acid is the more hydronium you have, or the more H+. Now, again, it's like a balancing act. If I have more hydronium, I have less hydroxide. And let's think about that with bases. Bases have more hydroxide. Well, the more hydroxide you have, you're going to see the less hydronium you have. Again, kind of a cool balancing act, and this is all because it's happening in water. Again, why water is so special. All right, so let's take a look at this image. I think it's really helpful to visualize what's going on. So in neutral water, you obviously have tons of water, which I'm not drawing, and you have hydrogen and hydroxide ions. And for each one, right, we have an equal amount of the other. And just remember, those hydrogens are hydronium, and sometimes we call them protons, and because we like to confuse you in chemistry, that's what's going on. Take a look at the acid now. In an acid, we're going to have more hydrogen, right? More hydronium. So if I was trying to visualize this, I might have, right, instead of 2 hydrogens and 2 hydroxides, I might have 3 hydrogen ions and 1 hydroxide. It's not to say that there's no hydroxide, but there's just much less now. Think about that as we apply it to the base. We're going to see that same concept, except instead of more hydrogens, now we have more hydroxides. So the neutral, right, I had 2. Well, now a base would have more hydroxide than hydrogen. Are there still hydrogen ions? Absolutely. There's a smaller concentration of them. So let's take a moment and summarize. If you're given values, if your solution has more hydronium or hydrogen than it does hydroxide, it is acidic. If you have equal amounts, you're dealing with water. It's neutral. And if you have more hydroxide than the H+ or H3O+, it's basic. Now this formula is going to show us the math behind it, and I'll get into some math examples later, but hopefully just, again, making meaning out of this. We compare everything to water, and this 1 times 10 to the negative 14th is a constant that we've derived from water. And if we're dissolving acids and bases in water, we can always compare it to 1 times 10 to the negative 14th. And so let's think about that, right? If I dissolve an acid, which causes hydronium to increase, well, they always have to equal this value when they multiply each other, which means hydroxide decreases, similar to what we've seen like in that image that kind of compares the amounts you have. And the opposite is true too, right? If I put a base in there, which causes me to have more hydroxide, well, again, when I multiply them by each other, they have to equal 1 times 10 to the negative 14th, which means I'm anticipating a lower amount of hydronium. Hopefully this helps you, and I'll be working some examples in some follow-up videos. Have a good one.